All right, Kourosh. This is the second time I'm going through this, and I realize that it's very difficult to understand with just me talking. But I don't think I could do any better than that. So why don't you just like take what you can from what I'm going to be saying over the next 10 minutes or so, and then if there's any points of confusion, we could talk about it in class tomorrow, or on the bus, or wherever it is you want to do that. So first of all, this is a portion of the grader algorithm which is on the board, which I believe I sent you a picture of, and the Kimia is doing part two, which is create all the puzzle pieces. Then she's doing part three, which is to use those puzzle pieces to create all the unique rows. And we do want unique rows because if there are double rows, then it's no longer USP. Okay, so then she is going to give us the unique rows, and then we are going to take them and create all the non-trivial matrices with a set number of columns, right? So that's where we start here in main. What this is saying here is we're hard coding a set. It's a 2D array, an array where every element is an array, and each of these represent a unique row. We don't have Kimia's algorithm yet, so we just hard coded 5 rows in here. And what we will have would be get Kimia, right? We would run that. Kimia would run her algorithm, return the 2D array of rows, and then Kimia rows would be equal to those rows, right? But for now, we are just hard coding them in as so. And then we're going to take those rows and we're going to give it to make matrices. Make matrices is going to take that, create a 3D array of unique matrices using those rows, and that's what all matrices is going to be, and job done. Because then we're going to take that and we're going to hand that off to Nick, and he's going to do whatever it is he's going to do to it, right? Which I believe is to decompose it into 1s, 2s, and 3s, run all the possible row swaps or row permutations, and then check if they're all USP. Because that is a definition of USP. It's that for every mate. No, what is it? No, it's that given a matrix, if you decompose it into 1s, 2s, and 3s, and you do any permutation, any non-trivial permutation on the 2s or the 3s, keeping the 1s fixed, and if that results in a strong USP, then you're good. And what is strong USP? I'm sorry, my definition is getting messed up. What it is given all possible non-trivial row permutations, they are all strong USP, right? Every single one is a strong USP. And so what is a strong USP? It's one where at least one, where there's no overlap. Where at least one cell in the matrix has an overlap of 2 elements. Okay, so that's that. Now we're coming back to our code. And so we're over here in make matrices. It's taking in the row pieces. The first thing that we're doing is we're taking those row pieces and we're making indices. What's that doing? It's taking this and it is assigning each row a index and putting it into an array. So since here we have 5 pieces, 5 row pieces, calling that 0, 1, 2, 3, 4, stuffing that all into an array of size 5, where the first element is equal to 0, second element is equal to 1, 2, 3, 4, and we're giving it to arg, right? Okay, now R we are defining as rows wanted. Of course, we set it at 3 for now, but of course we want to set to 17 and run it and see if it gives us anything. And then we got the n, which is how many are available. So like when it comes to combinations, the way the terminology is 3 choose 9. That means how many ways can you choose out of the 9 to create sets of 3 that are unique, right? That's combination. Permutation, uniqueness doesn't matter, right? But combination, uniqueness does matter. So that's what we're using here with the R and the N. The R is how many rows are wanted, and then the N is how many pieces do we have available to choose from to create that matrix, right, of size R. So we want R choose N. And Kimia, so first thing we want to do is create our empty book of 3D arrays, right? And that's what we're doing right here, creating our empty 3D array. We got to give it a size because arrays are static and you have to give them a size. I'm not sure if this is valid or not, but Jinzi said that this is the possible number of combinations of R choose N, this equation. So we're going to have a book with this many pages, and it's going to have this many rows, right? That's going to be 17. That's rows wanted. And the width of the page is going to be the length of the row pieces. So it's going to be 3 right there, right? So then this is going to be 17. This is going to be 3 in our case here. Of course, that's not going to be true when we run it on the actual algorithm, because I believe this is going to be 6 on what Umans was challenging us with. And so then that creates this empty book called combo arg, and now it's the correct size. So now the problem here is now we want to fill this book up with unique matrices using the row pieces, right? And so how do we do that? Well, that's where this combination algorithm comes in to play. What does it do? It takes in our arg, which has the numbers that are associated with the different rows, 0, 1, 2, 3, 4. And it has the N and the R. And what this is going to do is it's going to print out something that looks like this. Man, where is it? Okay, right here. It's going to compile, run. It's going to print out something that looks like this. Okay, and what is this? This is all possible non-trivial, well, by definition, combos are non-trivial combinations of 0, 1, 2, 3, and 4. Okay, so this is good. This is what we want, but we're not done yet, because we want to take this data and using it, we want to create a matrix. Each of these elements here represents a matrix, right? And we want to create those matrices so that we can pass it on forward to the next part of the algorithm, which is going to decompose them into 1s, 2s, and 3s, run all the possible permutations on the rows being switched around, and then the matrices being recompiled back together, and see if there's any overlap and all of that stuff. So what is this thing? It represents a matrix. And what is the matrix? It means first you're going to have the 0 piece, then you're going to have the 1 piece, then you're going to have the 2 piece. The 0 piece, the 1 piece, and the 2 piece. That's going to be the first matrix according to this data. What's going to be the second matrix? It's going to be the 0, the 1, and the 3 piece. So 0, 1, 3, right? And so on as you work your way down. And so where we left this off, where it has landed on your lap, is you're going to now need to take this data and you're going to need to use it to fill up this empty book with the rows, creating the matrices. And then when you're done with that, you're going to return the 3D array, which is the filled up book. And if you got that done, then you're done, right? So you could see here that we have most of this done. And then, there's maybe 30% that needs to be worked out on the back end. And of course, I'm here to support you and all of that stuff. And I guess there's one more thing I want to say before I leave, is that I used this algorithm here that I found on the web to calculate the combinations. But this uses a recursive algorithm to create the list, right? And we don't want a recursive algorithm to create the list because that makes it a little bit more difficult to stick it into a 2D array. So then I jumped on the web and I found this algorithm that does not use a recursive algorithm to create this, right? And the only problem here is that this algorithm here returns a linked list, right? But you can very easily change a linked list to be a 2D array and return a 2D array instead. And so you're going to want to take this code here and take out this code and replace it with this code here, right? So take this and replace this highlighted portion. And then you can move forward and try to get this all done. And I'm sure when we get it all done, put it all together, it's not going to work. So we're going to have to debug it and see what's wrong with the way we put everything together. But that's where we are at now. And I'm going to email you this code here. And then I'm also going to email you this here. So